Okay, well, thank you very much for the introduction. It's my pleasure to give a talk here. And well, congratulations, Alessio, first of all, because my pleasure to give the talk in honor of the Fields Medal. I'm very happy about that. And yeah, I mean, we've been, first time I met Alessio, I probably was at the conference. Then I was a postdoc in Austin for 3 years, 2 of which I was working with Alessio in Austin. And then I've been now 3 years in Zurich, also working with Alessio and Joachim. And then, well, now recently, since last month, I'm now in Barcelona, but I hope I can keep working with Joachim and Alessio in Zurich once the government allows me to travel. That I don't know when will that be. So anyway, so I want to present some, well, I was going to say recent, but it's not even recent because it's a forthcoming work, joint work with Alessio Figalli and Joachim Serra, and it concerns the Stefan problem. Okay, so I will talk about free boundaries. This will be somehow related to the previous talk of Joachim. But the Stefan problem, as we will see in a second, it's a parabolic problem. So it's an evolutionary version, it's an evolutionary free boundary problem. And some questions are somehow the same, like you want to understand what happens to the singular set, but the answers are somewhat different. And also the proofs that we will see will also be different. So let me start by introducing the Stefan problem. Okay, so the Stefan problem is probably the most classical example of a free boundary problem. And it dates back to the 19th century, and it describes the melting of ice. So here we have a simple picture that shows you, like, to have an idea, a mental picture of what to think about when you think about the Stefan problem is some ice, so it's like solid and liquid phases. You have 2 phases, and then you have that the ice is melting. Okay, so you have, in this case, you would have some boundary conditions here, but the important thing, what we are interested on, is on the free boundary, how this interface between the solid and the liquid is evolving. Okay, and then in the simplest case, which is the one-phase problem, we have a temperature that we assume it's 0 here in the ice, and it's positive, of course, in the liquid water. And then the temperature solves the heat equation here. Okay, so we all know the classical heat equation. It's a linear equation, very simple and classical. The problem here is that this is nonlinear because the set in which the heat equation is satisfied depends on the solution itself. So the temperature theta, okay, which is the unknown of the problem, appears also here. So the heat equation is solved in this set, okay, in the liquid water, and we have we need an extra condition, which is the one that determines how does this free boundary evolves. So how does this unknown set evolve with time? And then this free boundary condition basically is this one, and it's saying that the velocity at which the ice is melting is proportional to the gradient in space of the temperature here. So the more temperature you have nearby, the faster the ice will melt, which is very reasonable and natural. Okay, so this is the classical Stefan problem, okay, the one-phase Stefan problem. And then one very, very nice and useful transformation that you can, it's a very nice observation due to Duvaux in the 70s, so quite recently in a sense compared to the age of the problem. So in 1970s, it was observed that if you you define the function u to be the integral of the temperature in time, okay, then this function u, it in a sense encodes all this information. These 2 equations are encoded in a simple semilinear PDE. Okay, so the integral of the temperature that I will call u is non-negative, is monotone, non-decreasing in time, and it solves this PDE, which is that the heat operator equals to the characteristic minus the characteristic function of the set where u is positive. Okay, so basically, this is saying because the heat operator is a characteristic function, is in particular bounded, so the function will be C1, and then moreover, the heat operator will be 1 here and 0 here. Okay, so when I say here, I hope you can see my mouse. Is it correct? Okay. So basically, so let me, in the next slide, let me explain it in a bit more detail. So this is the equation that we have. Okay, so heat operator equal to minus the characteristic function, and you non-negative. And this is the same as saying that you have a non-negative function in a given set, okay, say B1 in the unit ball. And then this function satisfies two conditions. The first is that whenever the function is positive, it solves this very simple linear PDE. And on the boundary of the set where U is positive, okay, the gradient is 0. So we have a picture like that. And then this should remind us very much what Joachim was explaining the last talk, because the obstacle problem is exactly the stationary version of this. Okay, so all these equations and all these pictures that I have here, if you subtract if you remove like the time dependence, you look for just stationary solutions, then this is exactly the obstacle problem. But now we are interested in the parabolic version, okay, which is the Stefan problem, and we have this PD in the set where U is positive, and then a set that is unknown in which U is 0, and then a free boundary that is determined by either this condition, or you can look at it in this way. Okay, so this is the setting. So why do we study the Stefan problem or parabolic obstacle problem? And then one motivation is the melting of ice that I explained in the couple of slides ago. But there is another motivation that I also like, because it's like completely independent and gives you the exact same problem. So, and this comes from probability, and this is the optimal stopping problem. So basically, you consider a Brownian motion in a REN. Okay, so it's just like the simplest random process, stochastic process in a REN, and you have a given payoff function. Okay, so say that you have a function phi that is infinity with compact support and non-negative, say. Okay, and then you can run your Brownian motion. So and then it's running. You don't know where it's going, but then at any time, okay, anytime tau, you can decide to stop. Okay, you decide to stop now, and then you get a payoff depending on the point where you are. Okay, so if I stop at time tau, in which my Brownian motion was at point x, so tau, then I get a payoff which is phi of that point. Okay, so and then this is like a game in which you have a control, which is to decide whether you want to stop or not to stop. Okay, and then the game you want to play is, well, I want to maximize my payoff. So say that these payoffs are dollars, then I want to maximize my payoff, right? And then the question is, well, should I stop if we are at point? So if my Brownian motion has led me to a point x in a REN at time t, from 0 to capital T, so there is a deadline. Should I stop, or is it better to continue and hope for better payoffs in the future? Okay, and this is the game that is the optimal stopping problem. Okay, so this problem is like say well posed. So it has an optimal strategy, and basically the answer. So to find the answer to this question, you define the value function, which is you define v of x and time, which is the maximum expected payoff. So among all possibles of stopping time strategies, so tau is really like a strategy, that stopping time strategy. Among all possible strategies, what is the best expected payoff that I can get by looking at the future? So I don't know how it will evolve. I only know that it's a Brownian motion. Okay, this is all the information I have, and then I can decide whether to stop at present, or if I want to continue and then see if the future expected payoff is better than where I'm now, then I will. So the optimal strategy is to just not stop and let it continue until it goes to a better region of array. Okay, and then this function v, it turns out that satisfies three properties. The first one is that because I can always stop, then this v is always bigger or equal than phi. Then because I can always continue, in a sense, it's always it solves the heat. It's super harmonic, well, super caloric. Okay, and then it's also always caloric whenever I don't stop. And then these three conditions turn out to be equivalent to saying that this function v solves the obstacle problem, the parabolic obstacle problem. And then if I consider u, the function v minus phi, this will solve the Stefan problem in the formulation that I just wrote before. Okay, maybe with a right-hand side, but for simplicity, we take, as in Joachim's talk, just the characteristic function with no function f of x, say. Okay, so basically, the idea is that you consider the optimal stopping problem for the Brownian motion with a given payoff function. And then if this payoff function, say, is concave and then you make it 0 when it's negative, then you get that this function u being the expected, so the best expected payoff minus the payoff. Okay, this solves the Stefan problem in array. Okay, so either if you come from optimal stopping and probability, or if you come from phase transitions and melting of ice, you get anyway the same equation. So this is very nice because there is this analogy, and then it might be easier for you to think that in the ice, for example, when the region that was the ice, where u is 0, it's now in this case the exercise region where you should stop. You should exercise your payoff in a sense. I mean, you should stop and get the payoff now because it's better. Okay, and then these kind of models are used. I mean, this is a simplified model, but these kind of models are used in mathematical finance, and the typical example is the pricing of American options, in which you have this kind of games. You can stop or continue, and then you get free boundary problems. Okay, so this was just the motivation to study the Stefan problem. So let me go directly into the fundamental question that we want to understand here, which is the free boundary smooth? Okay, so the question here is the same as in the elliptic setting, and we want to understand if the free boundary in the Stefan problem is smooth, and to what extent is it smooth. Okay, so the first results in the 60s and 70s established that solutions are C11 in space and C1 in time, and this is optimal. Okay, so this is the best you can prove, and it's quite simple to prove. I mean, you can prove this in one page, basically. Okay, but then this is the first step to then study the regularity of the free boundary, right? So if you wonder what happens to the free boundary, well, then you have the first results by Kinderler and Nirenberg, which say that if you assume that the free boundary is C1 around the point, then it's actually C-infinity. So this is a bootstrap argument that is very typical in nonlinear elliptic or parabolic PDEs, that once you have some initial regularity, then you can kind of linearize your equation and then bootstrap and get smoothness. Okay, so here it's quite more challenging because it's a free boundary problem, so you don't have an equation for your free boundary, and then this is much more delicate than just Schauder estimates, say, but you can prove the same. Okay, so if the free boundary is initially C1, then it is actually C-infinity. And then this is the results on the one hand by Kinderler and Nirenberg, and then the real breakthrough, which is treating the nonlinear part in a sense of the problem of the free boundary regularity, was this classical breakthrough of Caffarelli, this classical paper of Caffarelli in Acta, in which he proved that the free boundary is actually C1 and therefore C-infinity, possibly outside a certain set of singular points. So while ice is melting, you can encounter, so you can imagine this is ice and this is liquid water, and then it's melting, so you can imagine a time previous, a prior time to that, in which everything is smooth, and then suddenly you encounter a singular point like this. So this is something unavoidable in a sense in the Stefan problem. So singular points will appear even for many initial configurations, say, and then you have singular points of this type. Okay, and then the result of Caffarelli say, well, either this happens, so either you find singular points like this, in which are always like cusps, or all the rest is smooth C-infinity in space and time, and the regular set is open in space and time. Okay, so this is all that can happen in terms of regular and singular points. Okay, and so the strategy of this, so this is the same paper in which Caffarelli treated the elliptic case. So because the proof of this is somewhat parallel for the elliptic and the parabolic, so the proof for regular points. Okay, and let me describe this proof very briefly. Okay, so the idea is to do blow-ups, and this is an idea that we saw in the previous talk in the elliptic setting. Now, in the parabolic setting, you have to do everything in the parabolic scaling. So you rescale your function u, you rescale it like rx and r squared t. Okay, and then you have a optimal regularity and some non-degeneracy that tells you that when I divide by r squared, okay, I consider this family of rescalings at the origin, say that the origin is a free boundary point, then this will converge to a blow up to a function that is u0. Okay, and then this function u0, I don't know how it looks like a priori, but the key difficulty in the theory, or one of the key difficulties in the theory, is to classify blow-ups. So what you want to say here is, well, I don't know anything about the free boundary, but let's try to do this kind of blow-ups, and then let me try to classify them and see if I can get information from them. And then the idea is that you can prove that these blow-ups will be well, actually, you can prove that they are homogeneous and that they are convex, and then using all this information, you can actually classify them and show the following. So you have these two options, and you see that even if this is a parabolic problem with a parabolic function, the blow-up, because we are doing this parabolic scaling, the blow-ups are always stationary, so they are independent of time. Okay, so basically what you see is that either you get a 1D solution, okay, which is this case. Either you get a 1D solution in which is the same solution as in the elliptic setting. It's a half space solution. This is what you expect at regular points, right? Because if you had a nice smooth domain, then when you blow up, you see a half space, okay? And the dependence in time disappears because of this parabolic scaling. Okay, this is what you expect when points are regular. So, and this is what we want to prove, but in the reverse mode. So you want to prove that I do this blow up, and then I can prove the regularity of the free boundary in this case. Okay, and then what Caffarelli did was to prove that either this happens, okay, either you get the 1D solution, or you get these paraboloids, which are the ones you expect for singular points. So there are only these two options: either a half space solution, a 1D solution, or these paraboloids that we encounter at singular points. Okay, and then once you have that, well, once you have this classification, the implication is the opposite in a sense. I mean, morally you are doing this implication, but the proof goes the other way around. You do blow-ups, you have these two possibilities, and then you want to prove that this implies that the point is regular. And in which sense? Well, we want to transfer the information from u0 to the original function u. So you want to say, if I get this blow-up, then the free boundary is C1 near regular points, and it looks like this. So my free boundary looks like this. So you prove that if you have a 1D solution of this type, then what you encounter in a sense before the blow-up was something like this. Okay, so this is the picture that we have at regular points, and this is well understood since the 70s with the theorem of Caffarelli. Okay, now the key question that remains open and still, I mean, it's what our result is about, is what happens at singular points. So at singular points, Caffarelli proved that these are the kind of blow-ups that we encounter. Okay, and then this is by definition, these are singular points. Okay, because they are non-regular. But then the question is, well, what can we say about singular points? Okay, so what can we say about singular points? And then keep in mind this picture, or even the pictures that are much more complicated that Joachim had in his previous talk. So of course, all the pictures that you can encounter in the elliptic case, you can find them in the parabolic case too. And then maybe even the parabolic case can be a bit more complicated, okay, because it involves the evolution with time. So you could have something else happening in a sense. Okay, so in 2D, the simplest case, in a sense, the simplest singular point is this picture, in which you have only one singular point, okay, and then all the rest are regular points. But as we saw, you could have here like infinitely many cusps a priori. Okay, and then what can you say? So the first results in this direction were by, well, Caffarelli in the elliptic setting, Monod also in the elliptic setting, and Blanchet, who was a student of Monod, and then used the ideas of Monod to prove the following result in the parabolic case, which is basically that you can find a Monod-type monotonicity formula for the parabolic setting. Okay, and then this result basically, and roughly speaking, I'm not being very precise here, but it says that in space, okay, so if you look at the singular set in space only, then singular points are contained in an n-1 dimensional C1 manifold. Okay, so this is if you look at the singular point in space. So this is the regularity in X, in a sense. But this is not what was proven in time. Okay, so this is in space. Let me see in a second what happens when you consider the regularity in time. Okay, then this is the classical theory, in a sense, of Caffarelli, Monod, and Blanchet. And then the idea is to prove, I mean, this is almost equivalent that to this with a specific model, with a non-explicit modulus of continuity, but uniform modulus of continuity here, that says that if the origin is a singular point, then your solution U looks like exactly the blow up, okay, which is a quadratic polynomial plus a small error that has the parabolic scaling embedded in. Okay, so the error is quadratic, so subquadratic, superquadratic in space and sublinear in time. So it's small o of x squared and t. Okay, so the error, in a sense, is much smaller in space than in time. This is why, and this is because of the parabolic scaling that you do in blow-ups and in the monotonicity formulas that are hidden here. Okay, so this is the in a sense the classical theory for the Stefan problem, including the singular set. Okay, and this is the everything that was known until very few years ago. And now in the elliptic setting, several improvements of this result have been obtained in the last years, including, well, the results of Weiss that prove that in 2D you can improve this only in the elliptic setting by a 2 plus alpha in 2D. Then Colombo, Spolaor, and Velichkov, who proved that in all dimensions you can put here not only an explicit, I mean, by compactness modulus of continuity, but a very explicit modulus of continuity, which is a logarithmic one. Okay, and then the results of Alessio and Joachim that we saw them described in the last talk, that basically prove that in the elliptic setting you can put here like constant x cubed, basically at almost all points, but not all points. Okay, this is and then we have our result with Alessio, Joachim, and myself, that we improved this and studied the generic regularity in the obstacle problem. Okay, but all these developments are in the elliptic setting, and then none of this was known for the parabolic. Okay, so what happens? Let's look at this. So this is, in a sense, the elliptic theory, and this is in a sense, the elliptic theory put it on the parabolic setting, and this is what you get. You get the C1 manifold in space. What about in time? Okay, so in other words, what can you say about the size of the singular set? Because the size now, I want to look at it in space-time. Okay, so this is why this involves the regularity in time. So the previous result of Blanchet implies that for every time, if you want, the singular set is contained in a C1 manifold of dimension n-1. Okay, so for every time, you have a C1 manifold if you want. Okay, and then this is still, and this is sharp. So you have examples in which for only one time, the singular set is really n-1 dimensional for one fixed time. Okay, so this is already, in a sense, a sharp theorem. But this is not saying, this is not telling you what is the size of the singular set in spacetime. Okay, so and in fact, the manifold that is constructed with this result, with the previous result of Blanchet, is C1 in space, But if you look at it as a manifold in a sense in space and time, it's only C1/2 in time. So because the scaling is different in space and time, the regularity is different in space and time, and it's always like divided by 2, the regularity in time. So you get a, in a sense, you get a manifold that covers your singular set, and this manifold is C1 in space, C1/2 in time. This is nice, but it's not really enough to get even that the singular set is n-1 dimensional. So this result does not imply that the singular set is n-1 dimensional when seen as a set in spacetime. Okay, and then the question that remained open for many years is, well, is the singular set n-1 dimensional in spacetime? Okay, so as a subset of Rn+1. So notice that also this is nice because so this result is saying, like, as in the elliptic case, right? So in the elliptic case, or in this case, if you look for a fixed time, you get that the singular set is contained in a manifold of dimension n-1. But the free boundary for a fixed time is also n-1. So the singular set is as big as the full free boundary. Okay, so and this is what happens. But in the parabolic setting, we can hope for something better because say the regular set in Rn+1 is the free boundary, the full free boundary is like n-dimensional. So if we can prove that the singular set is n-1 dimensional in space-time, this is really saying that in space-time, the singular set is already small, which is nice. I mean, this is something you expect, right? So in particular, this is saying if you have many singular times, you might have many singular points for one time, but not for every time in a sense. This is the first hint in this direction that we will discuss later on. Okay, so if you have many singular points for one time, this cannot happen for every time in a sense. Okay, and this is kind of hidden in this question. So is the singular set n-1 dimensional in space-time? This is the first question that we have, and that we will see the answer right now. Okay, and then the most natural way to measure this is in the parabolic distance. So this is a parabolic problem, and then this same happens as in the, I don't know, like the mean curvature flow, for example, in which you have the theorems of Ryan-White, for example, that measure the size of the singular set, and this is always in the parabolic Hausdorff measure, and then this is simply the Hausdorff dimension. This is simply the Hausdorff dimension associated to the parabolic distance, which is this one. Okay, so we want to answer this question here, and can we answer this question? And then yes, so we can completely answer this first question about the size of the singular set in our forthcoming work that hopefully will be on archive soon in the next few weeks, months. I don't know what to say. And then the result is the following. So if you get any solution to the Stefan problem that is not stationary, of course, otherwise everything is false. So if it's stationary, you go back to the previous talk, of course. If not, then this is the theorem. Okay, so if you have any solution to the Stefan problem that is not stationary, and you consider sigma to be the set of singular points, okay, so and I consider this set as a subset of Rn times R, okay, then the parabolic dimension of the singular set is at most n-1. Okay, and then as I said, this is the parabolic Hausdorff dimension of a set in Rn times R. Okay, so this is our first result that already solves this long-standing question about the size of the singular set. And notice that, of course, this number here, I mean, this constant n-1 is sharp because even for a fixed time, the singular set could be n-1 dimensional. Okay, so this is, of course, and obviously sharp, just because these kind of examples. And then what we need to prove here, so this is saying more than so parabolic Hausdorff dimension is even better than just the Euclidean Hausdorff dimension as a subset of Rn times R. And in particular, so the time axis has parabolic dimension 2. Okay, so because the time axis has parabolic dimension 2, then in 2D, what is this telling us in 2D? Well, in 2D, I get that the parabolic Hausdorff dimension of the singular set is at most 1. But because the time axis has parabolic dimension 2, well, in 2D, as a corollary of this, I get that the free boundary is smooth for almost every time. This is an immediate consequence of this result that is completely new. So this was not known even in 2D. Okay, so as you see, very little was known about the singular set here. And then this result gives us this consequence in 2D, that is that the free boundary is smooth for almost every time. So if you have singular points in 2D, then they are, I mean, the set of times for which they appear has measure 0. Okay, and then this raises the question of, well, can you prove something similar? Does the same happen in R3, which is the physical dimension, is the most natural dimension for the Stefan problem, if you think about the melting of ice. Does the same thing happen in R3 or not? And then more generally, how often do singular points appear? Can you have like estimates that answer this question in a way, I mean, similar to this result? Okay, and then in the same paper, we prove the following. So for the Stefan problem in 3D, in 3 dimensions, the result that we establish is the following. So if you have any solution to the Stefan problem in R3, again, that is not stationary, of course, then for almost every time, the free boundary is infinity with no singular points at all. Okay, so this answers the question that I raised in the last slide. That it's a very natural question of saying, like, do singular points appear often, or how often do they appear? And then it turns out that in dimensions 2 and 3, because of our new results, they don't appear too often, in a sense. So for almost every time, the free boundary is completely smooth, it's infinity. Okay, and then moreover, we can give an estimate, a better estimate on this. So if we define S as the set of singular times, and by this I mean the set of times for which you have at least one singular point, then the set of singular times has Hausdorff's dimension as a subset of R, has Hausdorff's dimension at most 1/2. So this is a fine estimate that we establish, and then we will describe the proof later on. But let me say just that we need a much finer understanding of singular points in order to prove this. So just getting the dimension of the singular set is not enough to prove this, and we need to go much beyond the current understanding of just doing the blow up and proving that it's a C1 manifold. We need to do much more in the spirit of the previous talk of Joaquin. Okay, but we'll see that the proofs are quite different. And then a second comment is, well, is the 1/2 sharp? Well, I don't know. Okay, so we don't know, but it's definitely a critical exponent for this problem. So we see that with our proof, we can see that this exponent 1/2 is really like critical. And if you want to prove a better exponent than this, you really need to figure out something quite different from what we do. Okay, so in a sense, this is critical, but it's not clear if it's optimal. But I mean, this happens in many problems. Even like if you think about the Navier-Stokes in 3D, there is the classical result of Caffarelli-Nirenberg, right? And then you get the same dimension. So the set of singular times has Hausdorff's dimension 1/2. Of course, the two results are completely unrelated, but it's nice that we get same exponents and same problem about is it, I mean, it's a critical exponent. It's not clear if it's sharp. Okay. And of course, the proofs have nothing to do with the Navier-Stokes. But I just wanted to say it as a short comment. So let's see the proof of the first result. Let's discuss next the proof of the estimate on the dimension of the singular set to start with. Okay, so what do we need in order to establish this estimate for the size of the singular set, and what are the techniques that we need to develop in order to prove this? Okay, so first of all, a nice observation in a sense, after working out our paper in the elliptic case, what we realized is that with similar techniques, so with cleaning arguments and barriers and stuff like that, in a sense, we realized that if we could prove something like that, that u of x, so the function minus the blow up, is like cubic at all singular points, where r here and in the next slides, r will be this modulus, I mean, this parabolic distance in a sense. If you could prove something like that, then by a cleaning argument that I will briefly discuss in the next slide. So by a cleaning argument, this would be sufficient in order to prove what we want. So basically, the first observation that we had was, well, if we can prove a better expansion, in a sense, a better estimate for the convergence of blow-ups, then this might give us the estimate for the parabolic dimension, parabolic Hausdorff dimension. Okay, and then notice that here the previous results of Caffarelli and Monod and Blanchet give a small O of r squared. Okay, so the question is, well, can you improve this and get r cubed? Okay, so can you improve? So because the blow up is quadratic, small O of r squared is the first, I mean, the first rate of convergence that is non-trivial in a sense. And then the question is, well, can you improve this to the r cube or not? Okay, and then unfortunately, this is not true at all singular points, but we can, well, we will see in a second. Okay, so the first message is that this is not true at all singular points, but we still can manage to prove the dimension of the singular set. Okay, so what we actually need to prove, basically, because you already know that in space the singular set is n-1 dimensional. So because of the parabolic scaling, basically what you need to do to prove the estimate on the dimension is to say that if the origin is a singular point, say, then when you go to BR times, so for any time bigger than CR squared in balls of radius R, then there is no singular set. Okay, so this is the kind of cleaning, in a sense, that when I say a cleaning result, I mean this, that when you increase the time, so you look at ball BR and you wait for a time comparable to R squared, then the singular set is empty. This is the kind of result you want to prove. Okay, so this is what we want to prove at every singular point. Okay, and this is what would give us, as an immediate consequence, the parabolic Hausdorff dimension. Now, the idea is that if you have this estimate, okay, combining with a cleaning lemma that is in a sense analogous to the elliptic ones of our elliptic paper that Joachim described, then if we had this, we would get this result basically. So this is kind of easy, okay, once we have all the elliptic proof. So the problem is that this estimate is not true at all singular points. So we need to work much harder. Okay, and then basically we have to split the singular set into 3 pieces. And then I define sigma m, the set where the zero set of the polynomial of the blow up is m dimensional. Okay, so depending on the zero set of the blow up, if it has dimension m, then I call this singular set sigma m. Okay, and then what happens is that when this set is small, so when m is smaller than n-2, then this estimate, the original estimate of Caffarelli, Monod, Blanchet, it cannot be proved. So we cannot do nothing about that. Okay, so it is hopeless. You cannot do nothing. You can do nothing about it, and then this is what you get. But still, we can construct some better barriers, and then in this setting, we still can manage to get this actually with a 2 minus epsilon for every epsilon, which is enough. Okay, so in this case, then we are okay, even if we cannot prove any expansion. So this is interesting because if you think about the strategy of taking u minus p2 and so on, that I will describe in a second, in all this set, this is hopeless and you get nothing new. You get just the same estimate. Okay, and then in the most important case, which is the sigma n-1, this is the biggest piece, the biggest chunk of the singular set. Okay, and then in this piece, we can prove the expansion at most points. Okay, so this is in a sense the parabolic version of the result of Alessio and Joachim for the elliptic setting, but the result is somehow well, I mean, it uses the same ideas we will see, but it's somehow more complicated because of the parabolic scaling, the parabolic monotonicity formulas, and so on. Okay, but it's really, like, roughly speaking, it follows the elliptic strategy to do this. Okay, and then something different that we need to do here is that in the remaining ones, so in these points where this fails, okay, in points in sigma n minus 1 in which this fails, that they might exist a priori, then we need to understand carefully their structure. And by this, I mean, we need to understand some properties of the blow-up. For example, we need to prove that the blow-up cannot be independent of time, cannot be elliptic, then the blow-up will be always convex in space, for example. We need to use some properties of the blow-up and then use this in order to deduce that we still, even if we don't have this expansion, we still can get this cleaning estimate with a 2 minus epsilon again, actually. But this is enough. So combining these three different sets, we get, in any case, this, and this implies the estimate for the set of singular times. Now, let me, relating this to the talk of Joachim a bit, basically to establish these higher order estimates, we study second blow-ups. So you consider U minus P2, U minus the blow-up, rescaled with the parabolic scaling, and divided by a certain norm in parabolic cylinders. Okay, I'm not being very precise with the norm because it's not important. Okay, and then this converges to a blow-up, to a second blow-up that I call Q. Okay, and then to do this, I mean, to do this rigorously and to get convergence to a blow-up and to prove that the blow-up is homogeneous and so on, we need a suitable truncated parabolic version of Algren's monotonicity formula that we prove here. So, and it has to be parabolic, of course, but it also has to be truncated because otherwise it fails. So the clean, in a sense, the clean parabolic Algren's frequency formula doesn't work. You need to truncate it and work a bit with some exponential errors that do not matter too much. Okay. Then, if you do this, you do this procedure, and then in sigma m, when m is less or equal than m minus 2, we always get a quadratic polynomial again. So you did nothing, in a sense. I mean, this is really not telling us a better expansion because you get quadratic again, so you get no extra information. Okay, but in sigma n minus 1, then we can prove that q is actually a cubic function, and by cubic I mean 3 homogeneous of degree 3. It's a cubic function at most points via a dimension reduction using this Algren monotonicity formula. Okay, so we use this kind of typical arguments from elliptic PDEs and GMT and minimal surfaces here, but in the parabolic setting and with this truncated Algren frequency formula. Okay, so via a dimension reduction, we prove that Q is cubic at most points. Okay, now the big difference with respect to the elliptic case comes here, and is that the function Q that we get is not a polynomial. Okay, so this function Q is not a cubic polynomial, but is a function, say in the simplest case, is of this type. Okay, so the typical function Q that you will encounter is a cubic, also it's 3 homogeneous with the parabolic scaling. Okay, and notice that for t is negative, so all these blow-ups are done for t negative. So this has like a sharp wedge for t negative. Okay, so this is very non-smooth in a sense and non-polynomial, so it's non-harmonic, non-caloric, sorry. But on each side, on xn positive and on xn negative, it's a caloric function with a wedge on xn equals 0. Okay, so this is a big difference, and then this means that actually we can prove that if you try to continue doing blow-ups, which is something we do in the elliptic setting. So if you try to do an X blow-up, so say U minus P2 minus Q, okay, this is something we do in the elliptic setting to get higher order expansions or higher order understanding of the singular set. And then this completely fails in the parabolic setting. So this cannot work because Algren fails for this function. Okay, so while in the elliptic setting we manage to subtract the second blow-up and continue to do a third one, here it's impossible to use Algren because it's simply false. Okay, and this is a big difference. So up to cubic order, the proof, you could say, I mean, you can think that the proof is somehow follows the same strategy as in the elliptic case up to order 3. But now if we want a finer understanding of the singular set, we need to do something completely different. Okay, and then we need completely new ideas, and we want to go further, and we do need to go further because we want to prove the result in R3 that I stated before. That does not follow from this. Okay, so now I need to go further and try to understand better the singular set in order to prove my estimate for the set of singular times in 3D. Okay, and then so we are stuck at order 3 in a sense, and then from order 3 we can actually, with completely different arguments, we prove the following. So we can say much more about the singular set. And then the result that we prove, so this is for every solution to the Stefan problem that is not stationary, and then if sigma is the set of singular points, what we prove is the following. So there is a set sigma star, I will call it sigma star, which is a very nice set, such that sigma star is contained in a countable union of infinity manifolds of dimension n-1 in space and time. Okay, so this set sigma star is infinity in a sense, I mean up to countable union. And the complement, so sigma minus sigma star, is very small. It has codimension 1 inside the free boundary. So sigma minus sigma star has parabolic Hausdorff dimension at most n-2, plus sigma star is extremely nice. It's infinity, basically. So this is very rare, I would say, on theorems. I don't know of basically any theorem for a singular set in a problem like this, like a free boundary or minimal surfaces, that say that the singular set is infinity, say, up to a smaller piece. Okay, and this is basically what the result is saying. And this substantially improves all known results, and it's even better than our results for the elliptic setting. Okay, so the results that we needed to prove in the elliptic setting in our paper to prove the Schaeffer's conjecture that Joachim described, basically they do not give a infinite expansion, even though they, I mean, this is also true in the elliptic setting, but this is a different story, and then 2 PhD students are working on this in the elliptic setting, but the proof is completely different. So actually, this is completely different, and in spirit, the proof from the elliptic setting, and this is why the result is somehow different from the elliptic one. Okay, and so this substantially improves our previous results, and moreover, so basically in sigma infinity, I'm saying that we get a higher order expansion of order infinity. So this is the best you can hope for in sigma infinity, in sigma star. Okay, so basically, so the expansion to get this infinity regularity of the singular set, we get a corresponding infinity expansion. Okay, and the expansion reads as follows. So basically, what we prove, I mean, this is just for information. What we prove is basically that the solution looks like this. This is like 2 parts. Like you can forget. I mean, basically, this is, if you forget about the B plus and the Q and the B minus and the Q, this is really the blow up. So this piece only and this piece only, if you forget about these extra terms, okay, these 2 pieces are the blow up. If B plus and B minus are 0 and Q plus and Q minus are 0, this is the blow up. But then for the blow up, we can only get to order 3. Now what I'm saying here is, like, if you want to go to order K for any K, you need to add corrections. And then the corrections, this looks like 2 completely separate parts in which you have the positive part of this and the negative part of this. And then we have a term that is like a constant times T, a constant times 3. So this is like a traveling free boundary, a traveling front, and then another traveling front, and then Q that correspond to like curvature terms basically, and are higher order polynomials. Okay, so this is the kind of expansion that holds at most singular points, in a sense, in sigma star. So as I said, this gives also a much deeper geometric understanding of most singularities. So basically, these are 2 fronts that are collapsing at time 0. So in this sigma star, the only thing that can happen are 2 fronts that really are collapsing, okay, at time 0, and then Q, these polynomials Q correspond to curvature terms in space and time. Okay, so this is the idea, that our new expansion gives you understanding of a geometric understanding of singularities at most points. And then the dimension n-2 of the set sigma minus sigma star is sharp. This is important. And moreover, so for the proof of this, there are two steps. So basically, of course, we start with the set in which we already had an expansion up to order 3. Okay. And then there are two completely separate steps in our proof. And the most difficult one is to pass from order 3 to order 3 plus epsilon, say 3 plus alpha. Okay, this is very challenging step. Okay, and it's completely different from the others, and in particular, completely different from the elliptic one. And then this requires, I will not describe this for a matter of time, of course, will not describe this, but basically this requires a variety of tools. So we combine some GMT estimate, some GMT tools, PDE estimates, and then we also need to do a dimension reduction, okay, because we need to discard a set that has to be n-2, so it has to be smaller. So we need to do a dimension reduction, but all this has to be done without monotonicity formulas. So you cannot use monotonicity formulas, but still want the same kind of results. And then we managed to do all this in a sense using much more the maximum principal estimates and I mean much more PDE in a sense, combined with a certain dichotomy and some GMT estimates. And then this allows us to pass from 3 to 3 plus epsilon for a very small, tiny epsilon. Okay, and this is the most difficult part of the proof. And then once you are at 3 plus epsilon, the proof is completely different. And we can pass from 3 plus epsilon to r to the k for any k. And then this is a completely different argument that is basically an approximation argument. So the idea here is that once you have an estimate of order 3 plus epsilon, you see the two completely separate fronts already. So it's not exactly true, but the free boundary behaves as if you had two regular parts that are independent one from each other, up to some errors. Okay, and then you have to manage to prove the Symfinity regularity of these two parts separately at the origin in a way that that is new, of course, because the results for regular points do not apply here. So you need an approximation argument in a sense that gives you from 3 plus epsilon to r to the k for any k, so to Symfinity directly from C3 plus epsilon to Symfinity in one proof, basically. Okay, and so this is basically the rough idea of how we get this infinite expansion. And then once you get this infinite expansion, you get something very nice for this set sigma infinity. So sorry, at what time should I stop? I forgot which time did I start. So Jacopo, I cannot hear you. You are muted.
We have a couple of more minutes, and then we should have time for questions. We can add up to 1:30.
Okay. Sounds good. Thank you. Yeah. Okay. So once we have all this, this is basically the proof of the Symfinity expansion. Now, what does it say? What does it tell us in terms of the set of singular times, which is what we cared about at the beginning, right? So how does this imply our result for the set of singular times? Well, basically, what we have is that these expansions plus a cleaning argument that needs to be different from the elliptic one, actually. So this one is a bit different because it's a cleaning on the past, but let's say we have something like that. So if U has a singular point, so imagine this is space, this is time, and then imagine that, so say that this point is singular, okay? And then what we are proving with a barrier argument, kind of, is that if this point is singular, then all this set, so this function U at time t plus r to the kappa, okay? This has no singular points in a ball of radius r. So the picture is like here above this curve, there are no singular points at all, anywhere. Okay, and then kappa is arbitrary because k was arbitrary, basically, in the set sigma star. So in sigma star, we can take kappa going to infinity, and therefore the singular set is Symfinity flat. So the singular set in sigma star is Symfinity flat, and then in particular, we prove this. I mean, this is now a GMT lemma, which is quite simple. This implies that the projection of sigma star on the t-axis has 0 Hausdorff dimension. So in a sense, if you look at the t-axis only, you look at the dimension of the set of singular times, sigma star doesn't matter at all. Okay, and then the only set that is remaining is the other piece, which was smaller. Okay, so in particular, we get the following result in 2D. So this implies our result in 3D, but it also implies our result in 3D, which is, in 2D, which is the following. Let U be the solution to the Stefan problem, any solution to the Stefan problem, which is non-stationary. Then the set of singular times has 0 Hausdorff dimension. Okay, and this is because the sigma star has always 0 Hausdorff dimension in the projection on the time axis. And then in dimension 2, n minus 2 is just 0. So basically the proof in 2D and 3D is you split sigma into sigma star and sigma minus sigma star. And then you apply the previous results. The first piece, sigma star, has projection of dimension 0. And then this second piece has projection of dimension, well, n minus 2 over 2. Okay, and then in 3D, you get the 1/2. In 2D, you get this 0. And that's it. Okay, and then recall also that in 2D, so even in 2D, the regularity for almost every time is new. So, and then we are proving way better than this. So not only the regularity for almost every time, but the set of singular times has dimension 0. So it's almost countable, but we cannot prove countable. It's a nice open question to know if you can do countable here or not. Okay, but it seems quite difficult. Okay, so I think, and of course, in here, the expansion up toward infinity is essential in this result, and it's also essential in the proof of the 3D estimate for singular time. Okay, so this is all I wanted to explain, and then I will stop here. Thank you very much for your attention, for the opportunity to give a talk here, and congratulations to Alessia.
Let's thank Xavier. All right, questions?
Maybe I have one.
Please.
So there is I think it's very interesting that you could do this fine analysis blow up, as you were saying, right, without monotonicity formulas to help you. And there is, of course, in geometric measure theory, the problem of regularity for anisotropic, for general elliptic integrants, right? Where somehow the lack of a monotonicity formula is one of the major things that is usually mentioned to say, okay, that's why we don't have the same nice theory that we have for the area, right? Yes. So do you think there is something that you have learned on this problem that could allow to make progress on the anisotropic regularity?
Honestly, I don't know. I should look into the problem better because I don't know it well enough to answer, I guess. But okay. We should definitely think about that. There are also other problems, like other free boundary problems that are not so clean in a sense, or for example, even non-local. So the same thing that happens for minimal surfaces that you have, I mean, perimeters in a sense, that you have anisotropic perimeters, then monotonicity formulas are out of the picture. Same happens for non-local operators, right?
Sure.
I'm more familiar with that. Then, for example, if you consider the optical problem for anisotropic, an anisotropic operator that is not exactly the fractional Laplacian, then you have also problems in the sense that you don't have monotonicity formulas.
Yes, of course.
Problematic. But in that case, you have convexity, and then convexity helps a lot, and you don't have that in anisotropic perimeters, of course. So one more analogous question probably would be if you consider non-local, but like the one-phase problem, the elliptic, like the Bernoulli problem, which is the one-phase, like prescribing normal derivative equal to 1, say. But you look at it in a fully nonlinear setting or non-local setting in which you don't have monotonicity formulas. I guess these are all. There are many problems in which the lack of monotonicity formulas don't allow you to get the same results. Here,
and these are definitely closer in spirit to what you have already done. I agree. More PDE oriented proof.
but these are, I mean, the one phase is much more related to the minimal surface case probably. But so what we do here, we use, I mean, we can easily, we have a linear PDE outside of free boundary. So we still have a PDE and functions, and we subtract the ansatz that we have, right? I mean, I guess it's quite different from looking at perimeters, and I don't know. I'm not sure. I would say that the answer is no, but I don't know.
Thank you.
Okay, we have another question in the chat.
I don't know if Alessio or Joaquim want to comment on this question of Francesco. Maybe they have better ideas.
My impression is no, right? Because essentially we use monotonicity to reach higher regularity first. I mean, we have at least the first part, we have monotonicity formulas. It's from 3 on that we don't have it. But it's a different, and then we need to linearize in a different way the problem, right? We need to find a different way to understand what is the dominant term, right? Which is what Xavi said, you have 2 fronts and it's very smooth. In a sense, it becomes like you have 2 regular points, but in the one of Francesco's, you don't start, right? I mean, it's really, it's like doing the fully nonlinear version of our problem from the beginning, right? I mean, you don't go from 2 to 3. I mean, that it's really, which is a bit what Savin did, that he started to do that but still he needs to linearize to the Laplacian. Somewhere you need the linearization. So I don't think what we do is big. I don't think.
And in the optical problem, we always have like this convexity, and then we are subtracting a polynomial that we know it solves the equation. So still the difference satisfies the difference between the solution and the blow up satisfies an equation. And this is very particular of the optical problem, I guess. No?
Yes, and also, I mean, even for the elliptic, right? There is this paper by Ovidio Savin with, right? And there they still need to know that you have a fully nonlinear, but which can be a bit linearized in one sense to Laplacian, right? I mean, it has to be C1 regular. So that's the difficulty. So they're still in a linearization setting, and it's difficult, I guess, here because you cannot classify blow-ups. I mean, that's, as you say, the convexity is the crucial thing because you start to linearize. So I think it's different, unfortunately. I see that Joaquim is unmuted, so I don't know if Joaquim has a comment. No.
Well, there's also a question in the chat by Jonas Hirsch. Maybe I invite him to unmute, which is more a remark. I read. I think that Taylor showed that for elements in currents, mod 3, the singular set is infinity. As if one uses ideas of Simon and White, the same holds true for currents mod 3 up to dimension 7.
Okay, I didn't know that result. Okay, thank you, Jonas. Yeah. So so it's quite unusual, but I see that there are at least one other result of a singular set being infinity. Nice.